Okay, let's take a look at today's lesson. Today we're going to be looking at a concept called limits. Very exciting concept. We use limits in calculus quite frequently. So let's talk about the words that we would use to explain limits and the symbols that we use here. So in words, if the value of f of x approaches a unique value L. So this is a y value. L is a y value. As x approaches c from each side, then the limit of f of x as x approaches c is L. Now that probably sounds like crazy to you right now, but let's keep working with it. It's all right. This is what it looks like in symbols. The limit as x approaches some x value c of the function is equal to some y value L, which we read it as the limit of f of x as x approaches c is L. So that's just kind of some word symbols of what it looks like. Let's look at it graphically. What does it look like on a graph? So here's a picture. This just happens to be pretty simple, just a line, y equals f of x. And here's our value c. That's our x value. And what we're doing is we are approaching from the left and the right to c. So let's see. If I'm approaching from the right, I would be on this road. I'd be headed, from the right. I'd be headed to this location. If I'm approaching from the left, I would be over here to the left. I'd be on the, the curve, I call it the road, and we would be approaching this y value from the left and the right. Okay, so this is really the limit as x approaches c. So x is moving along both sides. It's approaching c. And that particular y value is going to be L. Okay, so we've looked at it with words. We looked at it with symbols. We looked at it with a graph. What I would like to do is talk about one-sided limits. I was kind of referring to that, approaching from the left, approaching from the right, approaching from each side. That's very important and significant for us. So let's look at one-sided limits. If we are looking at a right-hand limit, we're looking at the limit as x approaches. They're using the letter A. Don't let that bother you. Sometimes they use a C, sometimes an A. It doesn't really matter. It just stands for some constant, some number. So the limit as x approaches A from the right of f of x, the plus means that as x approaches A from the right, okay, from the right, we'd be coming this way. We'd be headed towards our x value, that c value. We'd be headed that way from the right. That's a right-hand limit. A left-hand limit, the limit as x approaches a from the left of f of x, this little superscript, this little negative, means as x approaches a from the left. So here we're going to be coming from the left. We're on the curve. We're approaching our value here from the left. So that would be the left-hand limit. And there's something really important for us, and as it goes with limits, and that is, in order for a limit to exist, a full limit, the right-hand limit and the left-hand limit must be equal. So for example, we would write the limit as x approaches a from the right of f of x would need to be equal to the limit as x approaches a from the left of f of x. This is pretty significant. Those have to equal each other for the limit to exist. Okay, so that's kind of an overview of limits. So we're going to be, if it sounds crazy, it's okay. Don't worry about that. This is the very first time we've talked about limits. We're going to be talking about them over and over again. And so this lesson, we're going to actually do limits graphically, which I think is pretty straightforward. So let's look at some examples. We have a few examples over here. Okay. So that's the technique we'll be working on today. There are other techniques to solve limits that we will eventually look at, but today we're just going to look at solving by graphing. And so let's take a look at our first one. So we want to look at the limit as x approaches 0 of cosine 2x. So remember way back when, I think it was Unit 2, where we learned how to graph trig functions? Yes, you're going to get to do that again. Isn't that exciting? We're going to get to graph again, and you'll get to do it again next year in calculus. So let's take a look at our graph. We're just going to graph like we normally would. So cosine, we know what cosine looks like, right? And that double angle, that 2, this 2 right here, means, if you recall, the period equals 2 pi over b, right? That's b. So our period is going to be 2 pi over 2. So the period for this particular function is just pi. So there we go, so pi. So one cycle would just be to pi. What we need to be sure is what we're really interested in is the graph around x equals 0. That's what we're really interested in. So I'm going to do my normal, one period that I would normally graph, but I'm going to extend it because I really want to know what's happening around x equals 0. So if you recall our cosine, positive 1, negative 1, remember cosine starts up and then goes down. So it's a pretty simple cosine graph. And on the other side, it would go like that, right? So I'm really, my focus is right in here. I want to know what's happening as x approaches 0 from the right. So from the right, what's happening? Which y value am I headed to? As I approach from the right side, I'm headed to a y value of 1. Coming from the left, I'm headed to a y value of 1. So just to kind of get that in our head, so the left-hand limit, and I'm writing this in pretty much like a shorthand notation. Writing out the full limit is something we will get to. I'm talking conceptually. We're just going to look at it conceptually. So the left-hand limit coming from the left, that y value is 1. And the right-hand limit, which means I'm coming from the right, that y value is 1. Since these two sides, the left and the right side, equal each other, then I know that the limit as x approaches 0 for cosine of 2x is 1. That's my result of this graph. Okay, so that's our very first example. All right, let's go to the second example. So we have cosecant. We do have a transformation. The period is just a normal period, so 2 pi, but we have a transformation. Hopefully we remember what this means, right? We would go left pi. So let's just work on that. So we would go left pi. Okay, our total, it's 2 pi, so that would take us over here to pi. That would be 1 full cycle. Let's remember cosecant is the reciprocal of sine. Okay, so up 1 and down 1. So sine would have started here. Remember how we used to draw the shadow, the little shadow sign, so we know how to create cosecant. So the little shadow sign would look like this, right? It would go up like this and down. Okay. So recall where it crosses the x-axis. Those are where we have asymptotes. Now I'm interested in pi from the right, so I really need to extend this a little bit more. Okay, so our cosecant graph would look like this. Okay, so we have a pretty good rendition of cosecant. Let's see, so we are approaching, x is approaching pi from the right, so we're going to be over here. We just need to attach ourselves to the curve. So this is our goal, right? We're headed towards pi. This is where we're headed, our x value. So we're headed this way. I'm headed from the right. What is happening? As I head towards the right, towards pi, there happens to be an asymptote at pi, so that makes me head right towards infinity. So from the limit as x approaches pi from the right of cosecant x plus pi is infinity. Now, what do you think would happen if they asked for the left-sided limit? What do you think would happen there? If they asked for the limit as x approaches pi from the left of cosecant of x plus pi, what do you think that would be? So let's look. We're coming from the left. We're attaching ourselves to the curve. We're coming from the left, headed towards, our x values are headed towards pi, but we're coming from the left. That would make us go to negative infinity, wouldn't it? That would be negative infinity. And we're going to two completely different places going from the right and the left, aren't we? We're going to, if we're headed to from the left, we're going to negative infinity. If we're headed to the right, we're going to positive infinity. What do you think that means about the full limit? What will we have to say about the limit as x approaches pi of cosecant of x plus pi? What do you think that would be? We really have a mixed results, right? We're headed to negative infinity from one side, positive infinity from the other. Because we're headed to two completely different locations, I would say that this is a D in E, does not exist. That's what I would say if we were looking at the full limit. Now, I want to clarify here. Just because we're going to infinity, that's not why it's a D in E. It's really important for us to indicate what direction we're going. If we were looking at a situation where from both sides we were going to infinity, then our answer would be equals infinity, although we all know we can't equal infinity. So that's just a little nuance I need you to be aware of. Alright, so let's look at our last example. I think that perhaps the notes that you have has an incorrect number down here. It should read as x goes to 0. So if you have, if you would just change that for me on your notes. So that should be as x goes to 0. Alright, so let's look at this graph. So we have, we're looking at tangent. So let's think about this. Tangent, this period is going to be altered, isn't it? So for tangent, the period is pi over b, right? Our normal period for tangent is pi. So that's my b. So the period would be pi over pi, which happens to be 1. Okay, that's a little weird, but okay. So the period is 1, so we would go negative 1/2 over here and 1/2 over here. Alright, so we know our asymptotes would be there. We know it would be up 1, right? This would be a transformation of up 1. So our tangent graph would look something like that. So if we're looking at coming from the left-hand limit, coming from the left, I'm approaching a 1. Coming from the right-hand limit, I'm approaching a 1. So then it is safe for us to say that the limit as x goes to 0 of tangent of pi x plus 1 is 1. Alright, so that is our very first lesson on limits, which is very exciting, and we will look at a different way to solve limits in the next lesson. But for this lesson, we're just looking at graphing. All right.